What's that compound called?
Phosphate.
Iron 2 phosphate, right. Iron 2 phosphate. So, what is the molar mass of iron 2 phosphate? Go. Okay, so everybody arriving at the same thing I am? 357.49. That's some heavy stuff. What are the units for this if we say it's molar mass? Grams per mole. Grams per mole. What would the formula mass be? Yeah, same number but in AMUs. Same number but in atomic mass units. Okay. Any confusion on this now that we do one together? Biggest things to watch out for, make sure that you realize that there are 8 oxygen atoms there. Make sure you realize that there are 2 phosphorus. So pay attention to the subscripts and how they interact. Know that if you've got subscripts inside and outside, you're multiplying them, not adding them. That's a common trip up. Okay, so let's build on this now. Do you want to do one more together, or are you good with this now? One more together, okay. What is this stuff called? Okay, so titanium 3 dichromate. Find the molecular or the molar mass of titanium. There isn't a molecular mass. Duh, it's ionic. Find the molar mass of titanium 3 dichromate. When you're done, you can glance up and see if you're getting the same thing I am. Okay, are you getting the same thing that I am? Okay. Not difficult. Like I said, the only real trip up is making sure that you've got the right number of everything. And, you know, not copying the wrong molar mass off the periodic table helps. I've done that myself. As I said, certainly by the end of the next chapter, you will have the common molar or atomic masses, molar masses memorized. You'll say nitrogen, 14.01. Carbon, 12.01. Oxygen, 16.00. You'll probably also have chlorine memorized. That's a common one. And probably sulfur, 32.07. Yeah.
Wait, do we have to round oxygen?
Yes. Yes. Yeah. And unless you're using, so a good question about rounding. Unless you're using the entire number, so you can use 15.9994. Is that what you did?
No, I just used 15.
No, that's incorrect, because this rounds based on that. So if you're rounding that up, it becomes 16.00. So it's always acceptable to use all the numbers. That said, I, as a matter of course and habit, take everything to 2 decimal places. It's, you know, fairly common, acceptable level of precision for the kind of stuff that we're doing. I mean, good heavens, the kind of measurement instrumentation that we've got, you wouldn't be able to tell the difference anyway. So I go to 2 decimal places. You are always welcome to use the entire number. Just write it down so that I know why you're getting a slightly different answer than I am. Okay, good with this? If you are rounding, make sure you're rounding correctly using the rounding rules. Okay, then let's move on. We're picking up here. So you know how to get the molar mass of a compound. And if you remember from way back in Chapter 3, what you learned was what's called stoichiometry. You were starting off stoichiometry, and what you were starting with was very basic compositional stoichiometry. Stoichiometry! It's a lot of fun to say. Compositional stoichiometry is about telling us how many moles of a substance are in a given amount of mass of a substance. How many atoms are in a 12.01 gram sample of carbon. That's compositional stoichiometry. So it's really of limited usefulness when it's applied to individual compounds. But if you can apply it, or to individual elements, if you can apply it to compounds, this is where you start to be able to do some real work with chemistry. So the exact same thing that you did in Chapter 3, GMA, Except now instead of atoms, it's formula units or molecules. But you can still use your GMA if you want. I find it easier. So let's practice going from grams to moles to molecules or formula units. And if I give you 250.0 grams, wait a second. Okay, so I'm giving you 100 grams of sodium chloride. I want to know how many moles of sodium chloride that is. What's the very first thing I have to do? It'd be nice to know the molar mass. Now, if we back it up to our old conversion stuff, what do we do first? Well, we put our given in the first box. So we can certainly do that, 100.0 grams of sodium chloride. And we know that we want to go to moles. We need to have the same units here to cancel. And we need to have moles of NaCl on the top. Well, at this point, this is when, the brain kicks in and goes, oh, yeah, you need the molar mass. So we'll do the molar mass, and I just do mine off to the side here. 22.99, yes. And 35.45, yes. Okay, so 58.44 grams per mole. The units right there give me the relationship. 58.44 grams in 1 mole. So I'm going to divide 100 by the molar mass. I'll shrink this and get it off to the side. So I get a raw answer of 1.71156.742 moles NaCl. What governs my sig figs here? The 100. How many sig figs are there? It's tough because it's all zeros. 4. This 0 is significant. It's a 0 after the decimal. It's telling you with what precision that measurement was taken. So we have 4 sig figs, 1, 2, 3, 4. 1, 2, 3, 4. So we're going to round that 1 based on the digit that comes after it. Which means since we're rounding that 1 based on the 1, it stays. So we have 1.711 moles of sodium chloride. Okay. Now, what if instead of moles of sodium chloride, I had asked you how many formula units there were? Oh, what? No. That's for molar mass. That's for molar mass. So if we want to know, remember, if we go from grams to moles, we can go to atoms using, what's that conversion factor? 6.2 times 10 to the 23rd. October 23rd is mole day. Everywhere. So if we were asking this same question, but instead of moles, we wanted to know how many formula units. So in other words, how many units of a sodium and a chloride ion are there in that 100 grams of salt? What would that look like? It would look a whole lot like this with one additional step. So, same thing. We're going to start with our 100 grams of sodium chloride. We know we're going to have grams of sodium chloride. If we're doing GMA, we always have to go through moles. We can't ever skip the moles. So we know that our center step will be moles of NaCl. Badly written, I apologize. So down here, units to cancel will be moles of NaCl. And up here, what will that be? Formula units. of NaCl. Well, actually, that's what we're going to get for an answer. That's where we're going to get our answer. Or, you know, FUs of NaCl. Very serious one. Okay. Thanks. All right, so we know that there's 1 mole for every 58.44 grams of sodium chloride, and we're looking for the number of formula units in 1 mole. Oh, wait. No, that is a conversion factor. Duh. How many formula units are there in a mole? How many atoms are there in a mole? How many donuts are there in a mole? How many donuts are there in a mole of donuts? A mole of anything is how many? 6.022 times 10 to the 23rd. Do you have a raw answer yet? Who's got a raw answer? Maybe you got something like that? And we got to fix the scientific notation. You can't turn it in that way. And I'm too pea-brained to do this without going, let's see, that would be going backwards, so 1.030 times 10 to the 24th formula units NaCl in 1 mole. That would be your final answer. Now that said, we don't use the formula units nearly so much once we're doing conversions with actual compounds because it's not as useful. If you take up physics and you are doing electronics and magnetic fields, you'll look at how many atoms are in like a section of copper wire to look at how many electrons, to look at a flow rate because it's actually governed by the chemistry of how many atoms there are. But, you know, beyond that, we don't use the formula units nearly as much. Did you get the right answer? My thought was that we would go on to percent composition. But what I'm going to have you do first is complete some of the practice for conversions with compounds in the book because it is a two-step process. You're finding the molar mass of the compound, then you're doing the conversion. They're pretty easy, but I want you to get some practice. What I'm looking at right now is we'll do percent comp probably tomorrow, and then Thursday you will have a quiz, a FIP quiz on finding percent composition. So that's the way I'm envisioning it all working. Yeah, so if you work on 30, 32, and 33 right now, those are good practice for what we just did, and then we can start right off with percent composition tomorrow.